Multivariate trees. In the case of a univariate tree, only one input dimension is used at a split. In a multivariate tree, at a decision node, all input dimensions can be used, and thus it is more general. When all inputs are numeric, a binary linear multivariate node is defined as fm of x, which is equals to Wm to the transpose times x plus Wm0, which is greater than 0, because the linear multivariate node takes a weighted sum. Discrete attributes should be represented by 0, 1 dummy numerical variables. Equation 9.19 defines a hyperplane with arbitrary orientation. See figure 9.8. Successive nodes on the path from the root to a leaf further divide these, and leaf nodes define a polyhedra in the input space. The univariate node with a numerical feature is a special case when all but one of W and J are 0. Thus, the univariate numerical node of equation 9.1 also defines a linear discriminant, but one that is orthogonal to axis xj, intersecting it with at Wm0 and parallel to all other xi. We therefore see that in a univariate node, there are d possible orientations Wm and Nm minus 1 possible thresholds minus Wm0, making an exhaustive search possible. In a multivariate node, there are 2 to the d times Nm choose d possible hyperplanes. This is the results by Murthy, Kasif, and Zosberg in 1994, and an exhaustive search is no longer practical. In figure 9.8 is the example of a linear multivariate decision tree. The linear multivariate node can place an arbitrary hyperplane, and thus is more general, whereas the univariate node is restricted to axis-aligned splits. So when we go from a univariate node to a linear multivariate node, the node becomes more flexible. It is possible to make it even more flexible by using a nonlinear multivariate node. For example, with a quadratic, we have fm of x equals to x transpose times Wm times x plus Wm transpose times x plus Wm0, which is greater than 0. And Guo and Gelfand in 1992 proposed to use a multi-layer perceptron, chapter 11, that is a linear sum of nonlinear basis functions, and this is another way of having nonlinear decision nodes. Another possibility is the sphere node. Devrois and Gyorfi and Lugosi in 1986. We define fm of x equals to the absolute values of x minus cm, which is less than or equals to alpha m, where cm is the center and alpha m is the radius. There are a number of algorithms proposed for learning multivariate decision trees for classification. The earliest is the multivariate version of the CART algorithm. It's proposed by Brayman et al. In 1984, which fine-tunes the weights Wmj 1 by 1 to decrease impurity. CRT also has a preprocessing stage to decrease dimensionality through subset selection, chapter 6, and reduce the complexity of the node. An algorithm with some extensions to CRT is the OC1 algorithm, which again is proposed by Murthy, Kasif, and Zosberg in 1984. One possibility, Low and Vanishsetako in 1988, is to assume that all classes are Gaussian with a common covariance matrix, thereby having linear discriminants separating each class from the others in chapter 5. In such a case, with k classes, each node has k branches, and each branch carries the discriminant separating one class from the others. Broadly and Artegov in 1985 propose a method where the linear discriminants are trained to minimize classification error in Chapter 10. Guo and Gelfand in 1982 proposed a heuristic to group k greater than 2 classes into 2 supergroups, and then binary multivariate trees can be learned. Lo and Shi in 1997 used two-means clustering in Chapter 7 to group data into 2. Udis and Alpedum in 2000 use LDA in Chapter 6 to find the discriminant once the classes are grouped into 2. Any classifier approximates the real unknown discriminant choosing one hypothesis from its hypothesis class. When we use univariate nodes, our approximation uses piecewise axis-aligned hyperplanes. With linear multivariate nodes, we can use arbitrary hyperplanes and do a better approximation using fewer nodes. If the underlying discriminant is curved, nonlinear nodes work better. The branching factor has a similar effect in that it specifies the number of discriminants that a node defines. A binary decision node with the 2 branches defines one discriminant separating the input space into 2. An n-way node separates into n. Thus, there is a dependency among the complexity of a node, the branching factor, and tree size, with the simple nodes and low branching factors. One may grow large trees, but such trees, for example, with univariate binary nodes, are more interpretable. Linear multivariate nodes are more difficult to interpret. More complex nodes also require more data and are prone to overfitting as we get down the tree and have less and less data. If the nodes are complex and the tree is small, we also lose the main idea of the tree, which is that of dividing the problem into a set of simple problems. After all, we can have a very complex classifier in root that separates all classes from each other, but then this will not be a tree. Notes. Divide and conquer is a frequently used heuristic that has been used since the days of Caesar to break a complex problem. For example, go into a group of simpler problems. Trees are frequently used in computer sciences to decrease complexity from linear to log time. Decision trees were made popular in statistics in Brayman et al. 1984 and in machine learning in Quinlan 1986 and Quinlan 1993. Multivariate tree induction methods became popular more recently. A review and a comparison on many datasets are given in Edits and Alpedium in 2000. Many researchers, for example Guo and Gelfand in 1992, proposed to combine the simplicity of trees with the accuracy of multi-layer perceptrons. Chapter 11. Many studies, however, have concluded that the univariate trees are quite accurate and interpretable, and the additional complexity brought by linear or nonlinear multivariate nodes is hardly justified. A recent survey is given by Rukag and Moimon in 2005. The omnivariate decision tree, which is proposed by Udis and Alpedin in 2001, is a hybrid tree architecture, where the tree may have univariate, linear multivariate, or nonlinear multivariate nodes. The idea is that during construction, at each decision node which corresponds to a different subproblem defined by the subset of the training data reaching that node, a different model may be appropriate and the appropriate one should be found and used. Using the same type of nodes everywhere corresponds to assuming that the same inductive bias is good in all parts of the input space. In an omnivariate tree, at each node, candidate nodes of different types are trained and compared using a statistical test. Chapter 19. on a validation set to determine which one generalizes the best. The simpler one is chosen unless a more complex one is shown to have a significantly higher accuracy. Results show that more complex nodes are used early in the tree, closer to the root, and as we go down the tree, simple univariate nodes suffice. As we get closer to the leaves, we have simpler problems, and at the same time, we have less data. In such a case, complex nodes overfit and are rejected by the statistical test. The number of nodes increases exponentially as we go down the tree. Therefore, a large majority of the nodes are univariate, and the overall complexity does not increase much. Decision trees are used more frequently for classification than for regression. They are very popular. They learn and respond quickly and are accurate in many domains. This is the results proposed by Murphy in 1998. It is even the case that a decision tree is preferred over more accurate methods because it is interpretable. When written down as a set of if-then rules, the tree can be understood, and the rules can be validated by human experts who have knowledge of the application domain. It is generally recommended that a decision tree be tested and its accuracy be taken as a benchmark before more complicated algorithms are employed. Analysis of the tree also allows an understanding of important features, and the univariate tree does its own automatic feature extraction. Another big advantage of the univariate tree is that it can use numeric and discrete features together without needing to convert one type into another. And the decision tree is a non-parametric method, similar to the instance-based methods discussed in Chapter 8, but there are a number of differences. Each leaf node corresponds to a bin, except that the bins need not be the same size as in Parzen windows or contain an equal number of training instances as in k-nearest neighbor. The bin divisions are not done based only on similarity in input space, but supervised output information through entropy or mean square error is also used. Another advantage of the decision tree is that, thanks to the tree structure, the leaf bin is found much faster with a smaller number of comparisons. The decision tree, once it is constructed, does not store all the training set but only the structure of the trees, the parameters of the decision nodes, and the output values and leaves. This implies that the space complexity is also much less as opposed to instance-based non-parametric methods that store all training examples. With a decision tree, a class need not have a single description to which all instances should match. It may have a number of possible descriptions that can even be disjoint in the input space. The tree is different from the statistic models discussed in the previous chapters. The tree codes directly the discriminants separating class instances without caring much for how those instances are distributed in the regions. The decision tree is discriminant-based, whereas the statistical methods are likelihood-based in that they explicitly estimate the probability of X conditioning on Ci before using Bayes' rules and calculating the discriminant. Discriminant-based methods directly estimate the discriminants by passing the estimation of class densities. We further discuss such discriminant-based methods in the chapters ahead.